multipath signal effect on the capacity of MIMO, MIMO FDM, and spread MIMO FDM. This is Avinash. I'm a fourth year student from ECE, and I'll be taking you through our presentation.
MIMO system involving multiple antennas at a receiver can offer capacities many times more than that predicted by Shannon capacity limit for a single input, single output system. This is a system model for spread over DM. So here, the output from channel coding and from the bits being mapped onto their corresponding symbols is sent into a serial parallel converter, whose output goes to a spreading block, whose output further goes to an IFFT block, where each of the amplitudes are mapped onto their respective subcarriers, which are again summed using the parallel to serial converter. And then we have the transmitted signal. The transmitted signal over the channel goes to the receiver, where the reverse process takes place. The below are the equations for the received signal and the channel capacity. We evaluate the performance of MIMO without ISI, MIMO with ISI, and MIMO OFDM and spread MIMO OFDM. Case 1. Let's consider a single user channel first. So this is a graph between the capacity and the number of receiving antennas. This graph follows from the equation shown here. As the number of antennas, receiving antennas increases, mod h square term increases, and hence the result follows. Now obviously in this case, the MIMO OFDM coincides with the spread MIMO OFDM, which is then followed by MIMO with ISI, and obviously MIMO without ISI is the ideal case, hence it gives the best performance.
This is a graph between the capacity and the signal to noise ratio, and as we observed from the previous equation, the capacity is directly proportional to the signal to noise ratio, and hence we observe the following pattern. We notice that for the same value of SNR, MIMO without ISI has the highest capacity, followed by spread MIMO FDM and MIMO FDM. Both of these systems have exactly the same performance, while conventional MIMO with ISI shows a degraded performance. Shravan would be taking over from here.
Thank you, Avinash. Here is a graph showing the variation of channel capacity with the amount of delay spread of the signal. The amount of delay spread manifests itself in the number of interfered symbols. Thus, for a conventional MIMO system with ISI, as the number of interfered symbols increases, the signal to noise ratio at the receiver deteriorates and thus the channel capacity decreases. But for a single user MIMO OFDM and spread MIMO OFDM system, the capacity remains constant irrespective of the number of interfered symbols. This is because when a single user uses OFDM, he makes sure that the data on the adjacent subcarriers does not overlap and interference doesn't happen. For a single user channel, MIMO OFDM and spread MIMO OFDM systems offer the same performance, but the difference between the two systems is very clear when you go to the multi-user channel. Here you can see the variation of channel capacity with the number of users in a multi-user channel. For a conventional MIMO system, as the number of users increase, the channel capacity reduces again due to degradation of the signal to noise ratio. And we have also seen the effect of the number of interfered symbols on the channel capacity. What's interesting to note is that the capacity of MIMO OFDM system reduces as the number of users increase. This is because when more than one user competes for the same subcarrier, the symbols from two different users might overlap and thus cause interference. This does not happen in the case of spread MIMO OFDM because every user is assigned a unique pseudo-random code using which he can decode his symbols. Thus, we have seen that MIMO systems provide a greater channel capacity than SISO systems while still obeying Shannon's law. When Shannon formulated his capacity theorem, he did not foresee the usage of multiple antennas at the transmitter and the receiver. There is thus a new upper bound on the capacity given by the channel capacity of a MIMO system without ISI. We have also seen that the channel capacity for a single user system improves by using more number of receiver antennas, that is ensuring more diversity, by making sure the signal to noise ratio at the receiver is high, and by also having a low value of the delay spread of the signal. We have also seen that MIMO OFDM and spread MIMO OFDM systems deliver equal performance for a single user channel, whereas spread MIMO OFDM shows a better performance in a multi-user channel. So how do we use the results obtained? For example, when two users communicate using mobile phone, it is like a SISO system because each mobile phone has only one antenna. However, we know that the capacity of SISO system is lesser than that of a MIMO system. But at the same time, we cannot include a lot of antennas on the mobile phone because integrating so many antennas over a small area is a difficult task, and we also require a greater power supply to feed to the antennas when they are transmitting. Thus, given an array of antennas, we must have an algorithm which chooses which antennas will be transmitting the signal and which antennas will be receiving them. The performance parameter in this case will obviously be the signal to noise ratio at the receiver.